Hi. So right now we're going to talk about the steps of the agglomerative hierarchical clustering technique. Now let's have a look at them one by one, and I'm going to have a bit of voiceover and explanation at each one. So first of all, at this technique, each observation starts by being a cluster on its own. So if we have 10 observations, this technique starts with also having 10 clusters. 10 clusters that each one has only one observation. Now, the second step is we actually have to calculate the distance between all the current clusters. And since we started with all clusters being just single observations, right now we have to calculate the distance between all these observations that we have. Okay, so the third step actually is that we have to merge the two clusters that actually have the smallest distance. So when we have these 10 observations that we've seen the distance for each pair of observations, then we will find out which pair of observations have the smallest distance, and then we will merge these two observations into a new cluster. And obviously that cluster will have right now 2 observations instead of 1. Now, the final step is a bit of it's not totally honest when I say it's a final step, because you're actually reiterating the previous 2 steps. So what you're actually doing as, let's say, the final step again, is you keep working on the previous 2 steps, step 2 and 3, until at the end you are ending up only with one cluster that has all the observations that you started with. So I think it's probably way better if you see this in a visual explanation with actual observations. So let's start with a really simple data set. Even though I only put simple data set on the top, it's actually a really simple data set. So in this really simple data set, we're going to focus with just observations with actually 2 dimensions. So you see here that each row is actually focusing on 2 different pieces of information, xi1 and xi2. In this case, actually, we have 6 different cases. You could actually think of this example as maybe, the variable 1 and variable 1 refers to the first test in a specific exam, and the variable 2 refers to the second test of a specific exam. How good or bad the student did on those 2 exams. And obviously here we're focusing on 6 different students. So we're looking at the 2 different exams that these 6 different students gave. So you could probably see that if I was the 4th student, it wasn't such a great performance at the start with 17 out of 100. I do a bit better with 27 later on, and essentially you could see which students did really well on which exam. Now it could be really of interest here that maybe we want to cluster similar students together. Maybe of our interest is to create some tutorials later on and focus on the students that didn't do really well and have different exercises for them, and also focus on the students that for whatever reason did really well and we want to test them on something even more difficult. Okay, so let's actually have a look at this example, because even though right now you are starting to think about this example, you have to also visualize it to get an idea of what's happening. So this is actually how our data set looks. So you see right here, you see observation 1 and 4, so this is the 1st and the 4th student. So it actually turns out that I wasn't only a person who didn't do really bad, because I said that I was the 4th student. There was another student who was kind of close to what I did. And you can see here that there are a couple of students that did really, really well, at least on the 1st exam. So on the 2nd exam, the only person who did really well is the 3rd student. And not a bad performance for the 1st exam, but really a really good performance for the 2nd exam. Now again, here, what did the agglomerative technique told us that we have to start with? We have to find the distance between all observations. And then later on, we're going to focus on the observations with the smallest distance, and then we're going to merge these observations together. Okay, so we have to think right now about distance. This is a really interesting case, because it's not just focusing on distance between single observations. We have to also think about distance between observation and another cluster that has more than 1 observations. What do we do then? We actually have a lot of different choices and a lot of things to work on. In this really simple case, we're actually going to take 2 specific distances. So at the start, we're going to focus also with the Euclidean distance to estimate the distance between any pair of observations. And secondly, we will use what is known as the complete linkage criterion to calculate the distance between clusters that obtain more than one observation. Really soon, all these things will become really clear. Trust me on this. It's totally okay if you feel that right now you cannot understand how you can find a distance between an observation and a cluster that contains 5 observations. So don't worry at all about that. So let's start right now with actually using Euclidean distance, finding the distance between each pair of observations. So this is actually a distance matrix. So this is a matrix that shows the distance between each observation and every other observation. So hopefully right now, even with me just blabbering on while you are looking at the distance matrix, you have noticed a couple of things. The first thing that you hopefully have noticed is that the diagonal of this matrix is 0. And that kind of makes sense. We obviously expect that the distance between any observation and itself, it should be 0. Another thing that I really hope that you've already seen is that the distance between observation 1 and 2 is exactly the same as the distance between observation 2 and 1. So you see here that in this case it was 68.21 in both cases. So we actually know that this matrix will be a symmetric matrix. So instead of looking at this matrix with 36 different numbers there, let's make it a bit more easy to our eye. So this is what we actually have to focus on. I've still left the zeros here just so you could know that the distance between any observation and itself is 0. But essentially what we have to actually right now be really interested in is the distances between any observation and any other observation. And what did the agglomerative technique said? That in order to find the next cluster, we have to focus on the distance that is the smallest one than the ones that we have there. Well, in this case, the smallest distance between any observation and any other observation is 6.03. And the two observations that have that smallest distance is observation 1 and observation 4. So essentially right now, this is really good because we have kind of finished with the second step. So right now we know where the first merge should be. So right now we know that observation 1 should merge with observation 4. And now there will be a new cluster that has these two observations inside. That's really good. That's also where the tricky parts kind of start. Let's have a look at those now. So right now we're going to have another matrix, another distance matrix, but instead of having 6 rows and 6 columns of just all the clusters of the observations by themselves, right now we have a kind of strange thing that essentially it's our first cluster. So our first cluster is comprised of observations 1 and 4. So this is our first cluster. Our second cluster is the observation 2. And our third cluster is observation 3. And our fifth cluster is observation 6. So right now we have to recalculate the matrix of these new 5 clusters. Okay. You probably have noticed some question marks on the matrix. Let's not worry for those right now, and let's focus on everything else. So again, all the zeros that we have there, well, again, they make sense. The distance between the cluster that has the observations 1 and 4 and itself should be 0. The same with all the other clusters. So these stay the same. So let's go right now at the second row of the matrix that focuses on the distance between observation 2 and all the other observations. In this case, 3, 5, and 6. And remember that all these observations are actually clusters. They're all by themselves. Okay. You will probably notice here that the values that we had on the previous matrix carry on this one. Well, the distance between 2 and 3 is exactly what it was before. These are 2 clusters that each one has 1 observation each. So we'll actually keep using the Euclidean distance to find the distance between these 2 observations. So everything that you see over here is exactly the same that we had on the previous matrix. The really strange, in a way, thing here is that how are we going to find the distance between the cluster that has these 2 observations, 1 and 4, and the observation 2? So how are we going to compute this distance? Well, the complete linkage criterion, as you will also see on the notes, what it actually has, it actually sets the rules for us for all these cases. So it actually tells us that take any observation that belongs in one cluster. So let's focus on this cluster first, that has 2 observations. Take any observation that belongs to this cluster and find the distance with any other observation that belongs to a new cluster. So right now we're going to try and find the distance between 1, 4 and 2. Okay, so we can find first the distance between 1 and 2, write it somewhere down. Then we can find the distance between 4 and 2 and write that also somewhere down. And the complete linkage criterion says that you should take the maximum of those distances as your distance between the cluster 1, 4 and the cluster that has the observation 2. Later on, visually, this will make even more sense. So don't worry at all about it right now. So let's have a look at what we actually had on the previous matrix. Well, on the previous matrix, we had that the distance between observation 1 and observation 2 is 68.21, while the distance between observation 4 and observation 2 is 70.21. And you have to remember what we said previously. We said that the complete linkage criterion sets the rule here, and the rule is you should take the maximum of those distances. So in this case, the distance between cluster 1, 4 and the cluster 2 is going to be 70.21. Having exactly the same rule, we are actually, it's really easy for us to write now all the question marks that we had at the first row to actually complete them with the actual values. We're going to do exactly the same thing. Obviously here for the 55.34, what we actually did is we computed the distance between 1 and 6. We wrote that down. Then we computed the distance between 4 and 6. We also wrote that down and then took the maximum. Now, a question that you may think right now, even though I don't want you to think about this question, but you may think about it when you first see this, is okay, right now we have another matrix. What are we going to do? This didn't help us at all. We found distances between a cluster that contains more than one observation and clusters that contain only one observation. What's the point? Well, again, the point is the whole thing that we started with. Right now, this gives us a new distance matrix, and right now we can focus on the smallest distance again and then do a new merge. So let's have a look at where the smallest distance is right now. So actually right now, the smallest distance is between, again, 2 clusters that each one contains only one observation. It's between cluster 2 and cluster 5. The smallest distance, again, 14.25. So what are we going to do in this case? We're going to do what we always do in this case is we're going to merge these 2 clusters into one. And obviously right now, at the next step, we're going to have a new matrix that has the cluster 1, 4, another new cluster 2, 5, and the clusters 3 and 6. So we're going to have 4 clusters in that sense. So let's go back a bit to where we started. We started with visualizing the dataset, and that's obviously really important. But it's not only really important because it gives us input to the structure of the data, it's actually really important to take it to the next step and start visualizing all the things that we did before with the distance matrices. So I'm going to start with the color red, and feel free, if you ever listen to me say that I'm picking up a color and that's not the correct color, feel free to laugh at me. I'm really bad at these things. I'm pretty sure though that this is red. So let's have a look first at this. So right now we said that the first distance matrix that we computed, it actually told us that the smallest distance between any 2 observations was between 1 and 4. And that's why we merged these 2 observations. First of all, before I do anything on the graph, let's have a look and actually make sure that this also kind of makes sense. Well, yes, I think between the 6 observations that we have right now, I think it's pretty obvious to the eye that the smallest distance is between 1 and 4. Okay, and what did we do then? We actually merged them into a new cluster. So I can do this in a sort of a visual representation here. So I can actually say that these two is where, let's assume that the first merge happened. So this is where the first merge happened. So what did we do afterwards? Afterwards, we computed the distance between this new cluster and all these other clusters that have one observation each. And we figure out that, again, the observations, the clusters that needed to be merged together was actually 2 and 5. So, and you see what I did there? I also didn't give you the name for that color. I will go with orange for that. So this is orange, and this is where the second merge. This is where the second merge happened. Now, here are where things become really interesting. I will try to continue the merges right now just by looking at the observations. Obviously here, what the algorithm does on the background, all the distance matrices that I showed you before, it continues until there is only one cluster with all the 6 observations inside. Right now, I'm going to do the step that I did with the distance matrix. I'm going to do this visually. So right now, let's see what we have first of all. We actually have 4 clusters. We have one right here that is comprised of observations 1 and 4. We have another one right here that's comprised of observations 2 and 5. And we actually have 2 more clusters. This one that is just observation 3, and this one that is just observation 6. So let's go back to the distance matrix without actually computing it. What does the distance matrix actually is there for? Is because we have to compute the distance between all clusters. Okay, so let's think about that. What is the distance between this cluster and this one? Observation that has observation 3. This is where we used actually the complete linkage criterion. So what did we say here is that we have to compute the distance between 1 and 3 and also compute the distance between 4 and 3 and then find the maximum. So hopefully here you are okay with realizing that the distance between this cluster and this one is essentially the distance between 4 and 3, because 4 is a bit further away, so I'm guessing the distance here will be a bit bigger. Okay, so what are we going to do right now to find the distance between this cluster and this one? Whoa, right now we actually have 2 clusters that have more than 1 observations. So this looks a bit tricky, but it's actually not. What we did exactly to find the distance between these 2 clusters, we're going to take it one step further for these 2. So let's have a look at what we're going to do here. What did the complete linkage criterion said? That we have to take every observation from one cluster and every observation from the other cluster, find its distance, then write that down somewhere, and then find the maximum distance. Okay, so right now what we're going to do here, we're actually going to have to compute 4 distances. We're actually not going to have to do anything because this is all going to be visually right now. But if we had to write this down, we would have to compute 4 distances. Which 4? Well, we would have to compute the distance between 1 and 2. We would have to compute the distance between 1 and 5. And then we would also have to compute the distance between 4 and 2, and also 4 and 5. Now, because I'm a bit bored and I also don't know the answer, I'm not going to compute the distances, but I'm going to see this graph and see, okay, so what's going to be the maximum distance? I think you're probably going to be okay with me saying that the maximum distance will be between 4 and 5. So that is the distance between these 2 clusters. So we found that the distance between these 2 clusters was the distance between 4 and 3. It's a specific number, but this is the distance. The distance between these 2 clusters is actually the distance between 4 and 5. And obviously the distance between this cluster and this one is, I'm going to say 4 and 6, the distance between observation 4 and observation 6. So now what have we done actually? We have computed the distances, the distance between this cluster and the other 3 clusters. So we've started right now computing the next distance matrix that I didn't show you earlier. We have to do the same thing for this observation. Well, we already have the distance with this one. We have to compute the distance with this one and the distance with this one. And we have to continue doing this until we have all the distances. Now again, I'm going to take this a bit visually right now, and I'm going to assume that after I've computed all the distances here, so I've computed this one, I've computed this one, and I've computed this one, and all the distances between this cluster and the other 2. Now I'm gonna take a stab at it and actually say that I'm going to take purple, by the way, and I'm going to say that the new smallest distance, hopefully you will agree with me, and hopefully I'm also right. It's not just important for you to agree with me, it's also important for me to be right. Hopefully you will agree with me and I'll be right that the next merge should be between this cluster and this one, observation 6, because I think that should be the smallest distance. Okay, so in this case we're going to have something like this, and that's going to be our third essentially merge right now. And right now this step actually takes us, we actually have 3 clusters. This is one cluster, this is another cluster, and this is the third cluster. So right now, again, what the algorithm does, it computes distances between all these clusters. Well, the distance between this one and this one, we already know it, is the distance between 4 and 2. And right now, let's again revisit what we were doing before. What is going to be the distance between this cluster and this one? It's again going to be the maximum distance between any observation here and this observation right here. So I'm going to say right now, I'm going to take a stab at it, and I'm going to say that the distance between this cluster and this one is the distance between observation 3 and observation 5. Okay, so I'm going to say that this is the distance between these clusters, and this is the distance between these 2 clusters. Okay, and the only other distance that we need to know right now is the distance between these 2, which I'm pretty sure again it's going to be the distance between 4 and observation 5, because this is what will give me the maximum distance. So right now let's take it back a step a bit, just also I can make this right. So I have 3 distances. One is right here, this one. The second one is right here, this one. And the third one is observation 3 with observation 5. And right now I have to merge the smallest one. Again, taking a stab at it, I'm pretty sure that I'm going to be correct, but let's take a stab at it. I'm going to assume that this is the smallest distance out of all these 3. And this is again where I was about to use the same color for the previous merge, so let's take it. Let's do it a bit better. And this is where actually the 4th merge is. And right now, hopefully, you are pretty confident with what the final merge will be, because if you think about it, there are only 2 clusters left. There is this cluster over here, and this cluster that contains all the other 4 observations. So right now, just so you could see another circle, a green circle right now, the final merge will be between these 2 clusters, and it's going to be looking something like this. So this is going to be our 5th merge. So I would totally understand you if you're saying, wait a minute, is this going to be the data visualization technique that we're going to use for agglomerative clustering techniques? No, but this will give you a really nice idea of where we actually merged clusters together. The first merge was right here, the second one was between these 2 observations, the third one was right here, the 4th one here, and the 5th one essentially was between all observations between these 2 clusters. So really soon we're going to see a dendrogram that does this, but probably 1,000 times better. So we just saw how to visualize the merges on a scatter plot. That is all well and done, but what happens when our observations are in higher than 2 dimensions? It's not going to be easy for us to produce a graphical representation of the data and then show the merges on that graph. Well, in that case, we could actually use a dendrogram, and the dendrogram works for any number of dimensions. And this is what we have right now for our example. So let's have a look at the dendrogram first. We see on the x-axis the 6 different observations that we started with, and remember that they started as clusters by themselves. And on the y-axis we see the height, okay, which that reflects the distance between these clusters. Okay, so if you remember again, or if you go back to the video, the first merge actually happened between observations 1 and 4, and it happened, I think the distance was 6 point something. I could be wrong, but I think it was 6 point something. So if you see what is happening here, this is exactly the same height, 6 point something. that these two observations merge together. So observations 1 and 4, they used to be two different clusters by themselves, and right now they merge together at the height of 6 point something. What happened afterwards? Well, afterwards we had observations 2 and 5 merging together into one cluster, and I think there it was 14 point something. So this is exactly what is happening on the dendrogram. It shows us at each height which clusters are being merged together, and obviously here at the start, at the bottom of the x-axis, we see all observations by themselves, because as you remember, all observations started by being clusters by themselves. So the first merge happened right here, the second merge happened right here. It actually turns out, and I'm really happy about this, it turns out that I was right to actually connect then observation 6 to this cluster, because this is actually what is happening, and this happens obviously at a bit of a higher height. I want to say 20 something, 23 point something. So we see that the cluster that had observations 2 and 5, right now it's a new cluster that has observations 2, 5 and 6. And then the next merge again was the observation 3 that was merged exactly at a distance of 65 point something with this cluster. And at the end, obviously, at this sort of graphical representation, we will have the final merge between the two existing clusters on that step. Now, what is also really important here, so for this example, we had 6 observations. Well, in these 6 observations, if you actually really think about it, we are actually going to have 5 merges. So if we have n observations, there is going to be n minus 1 merges. On the next video, you will actually have a better look at a dendrogram and an explanation of that in a real dataset.